Let's get started. Last session, we covered this paper, which was about super resolution, and super resolution has applications in the gaming industry and film industry. And for gaming industry, I'm sure you have heard of DLSS. It's a service that NVIDIA provides. It's for basically the technology behind it is a generative adversarial neural network. So it's the same GPU, but it's going to be able to process high resolution images because of adversarial neural networks. So that's the technology behind it. And that's deep learning super sampling, super resolution. And then we covered a theoretical paper on trying to improve Wasserstein GANs. We covered most of it. We reviewed GANs a little bit. Then we talked about Wasserstein GANs. We compared the two objectives, and we saw that there are similarities between the two. And then we said in Wasserstein GAN, an important factor was that we were looking at all of the neural networks that are one Lipschitz functions. And one way to enforce Lipschitz continuity was by clipping the weights of your critic. But then that seemed a little bit ad hoc because now you're changing the structure of your neural network. During training, whenever one of your weights exits a box, you're gonna clip the weights. But is there a way to enforce this Lipschitz continuity in a soft manner? And the idea is to use gradient penalty. There is a theorem which says that if you have a differentiable function, it is going to be one Lipschitz. It's going to be a Lipschitz continuous function with a constant of 1 if it has gradients with L2 norm that are at most 1 everywhere. So every single word in this sentence is crucial. First, it needs to be differentiable because you need the gradients. Then you need to compute the norm. And the norm has to be at most 1 everywhere. So you can start with the original critic loss. So that's our original critic loss. It's going to give you 1x tilde for the generator, 1x for the real data. And then you cannot enforce the gradient penalty everywhere because the space is huge, the space of images. So you cannot enforce it everywhere, but you can enforce it on the fly, on the line between the real data and the generated data. So you're going to keep sampling on that line. So not only you sample from your real data, not only you sample from your generated data, but you sample a point on the line between them and try to enforce this gradient penalty on that line. So this is a smart way of spanning your space. Otherwise, the space is too huge, and then it's not going to be possible to enforce this guy everywhere. Okay, that's exactly what I mentioned. So X hat is sampled uniformly. So it's going to be sampled according to a uniform distribution on the line between X and X tilde. Any questions up until this point? This we covered last session. So far, our data was in the form of images. And for images, your output is continuous. So your pixel values are a continuous variable. They can take numbers from 0 to 255, or if you normalize it, it's going to be from 0 to 1 or from -1 to 1, depending on how you normalize your images. But this is going to be a continuous variable. Now the question is, can you generate discontinuous data? And by discontinuous data, I mean data in the form of text, because then you have a vocabulary. Either you're using a character-based model or a word-based model. Whatever that you do, you're going to have a dictionary, you're going to have a vocabulary, and members of that vocabulary are your discrete values. Okay, you have only a finite set of outcomes that could happen. Can we use GANs for such a purpose, for modeling discrete data rather than continuous data? What are we going to do? Whenever you have discrete data, our generator needs to take as input a code. So it's a latent variable. So it's going to take Z, it's a vector, and it's going to output a sequence of vectors. And 32, let's say, is the length of your sequence. So if these are character-based models, you're outputting 32 characters, including the space. It's going to give you a sentence that is 32 characters long. So a vector goes in, a sequence of vectors is going to come out, and this we are going to model with CNNs. One-dimensional CNNs is actually the deconvolution. It's not a convolution, it's a deconvolution, but it's 1D. Now you're going to pass that information to a critic or to a discriminator. Rather than output, these are going to be one-hot vectors. Rather than pushing one-hot vectors through your critic, you can actually push the softmax, because now all of your variables are going to have values. One of them is going to dominate, it's going to have the biggest softmax value, but all of your variables are contributing, all of the entries of these vectors. And as I mentioned, these VIs, after you sample from your softmax, they're going to give you your words. They're going to be in the form of one-hot characters, one-hot character vectors. And they're n-dimensional, and n is the size of your vocabulary. I don't know, if you're doing English, maybe you have 32 or 26, okay? And your discriminator is going to take a sequence of vectors as input, and it's going to output a number. If you're doing a regular GAN, that's going to give you the probability. If you're doing Wasserstein GAN, it's just a number, a real valued number. Now you have two choices. One is to use GAN's objective function. The other one is to use Wasserstein GAN. It turns out that if you use GANs, it's not going to converge. And there are theoretical reasons for it. And I'm going to tell you why. But if you use Wasserstein GAN, it's going to converge. And it's going to give you some decoded samples. Now you're sampling from your generator. What are you going to get? You're going to get sentences that are 32 characters long. So it's going to be 1, 2, 3, 4, 5, 6. And if you count this, it's going to be 32. And these are samples. This is another sample. This is another sample. This is another sample, etc. Same thing here. This is another sample from this distribution. And the way that you're sampling is you're going to sample a Z vector from a normal distribution. You're going to push it through your generator. It's going to give you a sequence of probabilities. So there is going to be softmax there. And then you're going to choose the maximum. So you're going to do argmax to give you the corresponding character. Now, why is GANs not converging, but Wasserstein GAN is converging? Let's take a look at what we are modeling with the generator up there. Each vector that is coming out of the softmax is going to be n-dimensional. So it's going to have n entries. Each entry is positive, actually non-negative, and it's going to add up to 1. So these are probabilities. And this is going to give you a simplex in Rn. What is your target distribution? You're going to have one-hot vectors. And what is that? This is going to be, again, n-dimensional. They're still going to add up to 1. So they're going to be probability. But you only have 2 values for your outcome. So your entries are either 0 or 1. And we know that Vn is a subset of delta n. Okay, so far so good. If you evaluate the Jensen-Shannon divergence, then Jensen-Shannon divergence is for GANs, it's going to saturate on this space. So it's going to become 0. But your Wasserstein distance is still going to be a well-defined objective function. You're going to have values, they are non-zero, their gradients are non-zero, and you can optimize that. Okay, so you can use Wasserstein GAN to do discrete data. Any questions so far?
I have a quick question just about this text output.
Sure.
Is the result here just that we can model discrete data and it's semi-understandable, not that it's like doing any sort of a good job?
Yes, so the result is that you can actually model discrete data using GANs.
Okay.
But actually for discrete data, we have been doing it for half of the semester. There are better ways of doing it, like BERT, like GPT type models, the language modeling type models. Mm-hmm. Because they are conditioned, they're doing one word at a time. It's either one word at a time or one character at a time. Any other questions? But this is neat that you can actually model discontinuous data using GANs, because GANs are typically used for continuous data. But this is a neat observation that yes, it is actually possible to do it.